Lecture 28, Stress in the Subsurface. Since the surface of the Earth is in contact with a fluid, either air or water, which cannot support shear tractions, it is a principal stress plane. Thus one principal stress is normal to the Earth's surface. If topography is flat, one principal stress will be vertical, sigma v, and the other two will be horizontal, the maximum horizontal stress, sigma capital H, and the minimum horizontal stress, sigma h. Topography will of course modify this simple model. In a steep valley, for example, since one of the principal stresses is always perpendicular to the surface, the orientation of the principal stresses will rotate. In general, across the valley, the minimum principal stress will be perpendicular to the surface, and exfoliation joints will form parallel to the surface. These stress deviations occur near the surface only, but they must be considered when stress is measured near the surface or other free surfaces such as tunnel walls. At large kilometer depths, the simple model above generally holds. This model is very useful, because it allows us to fully describe the state of stress at depth with just four parameters, sigma v, sigma capital H, sigma h, and the azimuth of either sigma capital H or sigma h. However, there are some exceptions. Salt is one of them. Salt is relatively weak and it cannot support much shear stress. Therefore, the principal stress directions will bend near salt boundaries. This may have significant impact on drilling and wellbore stability. Weak fault or fracture zones can also deflect the stress field, because the fault or fracture sustains less shear stress. This of course depends on several things, including the normal stress acting on the fault friction, and fluid pore pressures. The vertical stress is easy to estimate. It is the weight of the overburden and is equal to rock density, times gravity, times depth. This stress is known as the lithostatic stress. This figure shows the vertical stress in Norwegian mines. For crystalline rocks, a good estimate for the gradient of sigma v is 27 megapascals per kilometer. In sedimentary basins such as the North Sea, a good estimate for the gradient of sigma v is 23 megapascals per kilometer. There are several methods to estimate stress, such as borehole breakouts, overcoring, hydraulic fracturing, and recent surface structures related to the current stress field. None of these methods measure stress directly, but they rather look at the effect a set of forces have on rock deformation, and from that they estimate stress. In this lecture, we'll look at borehole breakouts and hydraulic fracturing. To understand borehole breakouts, let's consider the problem of the stresses around a circular hole in a rock material. This is one of the most important problems in rock mechanics, since most holes drilled through rock are of circular cross-section such as tunnels and boreholes. This problem was first solved by the German engineer Kirsch at the end of the 19th century. The figure shows the principal stress trajectories around a cylindrical hole in a biaxial stress field. Sigma 1 are the continuous lines, and sigma 3 are the dashed lines. Where the trajectories of sigma 1 converge, stresses are more compressive. This occurs at the azimuth of sigma 3. Where the trajectories of sigma 1 diverge, the stresses are less compressive. This occurs at the azimuth of sigma 1. To solve this problem, we use a polar coordinate system as indicated in this figure. The hole has a radius, a, and the stresses are calculated at a distance, r, from the center of the hole. Any orientation is defined by an angle, theta, measured counterclockwise from sigma 3. The radial, sigma rr, and tangential, sigma theta theta, stresses are given by these equations. These equations are plotted here using Python code. The upper left figure is the hoop stress, the upper rift figure is the radial stress, the lower left figure shows the variation of these stresses with radial distance, and the lower right figure shows the variation of these stresses around the hole. Around the hole, the hoop stress is maximum at the azimuth of sigma 3, and it is minimum at the azimuth of sigma 1. However, the hoop stress decreases quite rapidly to the far field stress values. At the azimuth of sigma 3, the hoop stress reaches the far field value of sigma 1 at a distance 5 times the radius of the hole. The radial stress is 0 around the hole, and reaches the far field stress value at a distance 5 times the radius of the hole. Since in the hole, the hoop stress is maximum at the azimuth of sigma 3, and minimum at the azimuth of sigma 1, one would expect the rock to fail by compression near the azimuth of sigma 3, and by tension near the azimuth of sigma 1. This is what happens in a borehole. In the regions of maximum hoop stress, the rock fails by compression and shear, forming shattered rock areas called breakouts. Near the regions of minimum hoop stress, the rock fails by tension and develops tension cracks. This allows determining from borehole images the orientation of sigma 3, which if the borehole is vertical, is the orientation of sigma h. The figure shows breakouts in an ultrasonic borehole image, which appear as dark bands. The inset shows a cross-sectional view of the well made with televiewer data. Breakouts indicate a southeast-northwest orientation of sigma 3. The same principles apply to tunnels. Spalling of rock fragments in certain parts of a tunnel gives information about the orientation of the principal stresses, sigma 1 and sigma 3. What about the magnitude of the minimum horizontal stress, sigma h? To estimate the value of this stress, we can run a hydraulic fracturing test called the leak-off test. In this test, an open section of the well is pressurized to the point that a hydraulic fracture is created, and the magnitude of the least principal stress can be determined. The pumping rate into the well is constant. Thus, the pressure should increase linearly with time as the volume of the well is fixed. At the pressure where there is a distinct departure from the linear, which is the point LOP in the graph, a hydraulic fracture must have formed. This is because the fracture increases volume and affects the rate of well pressurization. The hydraulic fracture is always perpendicular to sigma h and parallel to sigma capital H. The peak pressure reached during the test is termed the formation breakdown pressure, FBP, and it represents the pressure at which unstable fracture propagation away from the well occurs. That is, the fluid flows into the fracture faster than the pump supplies it, hence the pressure drops. If pumping continues at a constant rate, the pumping pressure will drop after the FBP to a relatively constant value called the fracture propagation pressure, FPP. This is the pressure associated with propagating the fracture away from the well. The FPP and LOP are supposed to be equal and they are very close to sigma h. Therefore, from borehole breakouts, we can estimate the orientation of the horizontal stresses. And from leak-off tests, we can estimate the magnitude of sigma h. The magnitude of sigma capital H, however, is more uncertain. An important factor we need to consider is pore pressures. Rocks can contain fluids in their pore space. If the fluid is water and is connected to the atmosphere, and if the groundwater table is at the Earth's surface, the pore pressure, P, at any depth is the density of water, times gravity, times depth. This is known as hydrostatic pressure. When the fluid pore pressure has this value, it is said to be normal. At a depth of 1 kilometer, the hydrostatic pressure is about 10 megapascals, that is, the hydrostatic pressure gradient is 10 megapascals per kilometer. The ratio of the pore pressure, P, to the overburden pressure, sigma V, is known as the pore fluid factor, lambda. This factor expresses the fraction of the load borne by the fluid. If lambda is 0, the entire load is supported by the rock. If lambda is 1, the load is entirely supported by the fluid. For normal, hydrostatic pressure in a sedimentary basin, lambda is about 0.43. Abnormal pressures are regularly encountered in deep oil wells, where values of lambda as high as 0.9 have been observed. Several mechanisms may contribute to such abnormal pressures, but the main reason is that the permeability of clay shale is so low that when these sediments are buried and compacted, the water escapes very slowly and the fluid pressure rises. This is an example from an onshore field near the Gulf of Mexico, in South Texas. Hydrostatic pore pressures are observed to a certain depth of about 8,300 feet. A transition zone is then encountered in which pore pressure increases rapidly with depth, and high pore pressures, lambda equal to 0.9, are observed at depths larger than 11,000 feet. The red dots in the figure are pore pressure data from the southern North Sea. Below 3 kilometers or so, pore pressures are above normal, and at about 5 kilometers depth, pore pressures are close to lithostatic, that is, lambda is close to 1.0. Since fluids do not support shear stress, pore pressure affects only the diagonal components of the stress tensor. In other words, the normal traction on any plane is reduced by the pressure P, while the shear traction remains unchanged. Sigma prime is known as the effective stress. Worldwide stress measurements are compiled in a global dataset called the World Stress Map. This map displays the orientation of the maximum horizontal stress, sigma capital H, colored by faulting regime. We will come back to this dataset later when we discuss the mechanics of faulting. To learn more about this, read Chapter 5 of Fossen and do his e-learning module on stress. And answer these questions.